Calculus BC, we're looking at section 6.5, and there's a lot packed in here. Look at our first learning target. I can apply the mean value theorem for integrals. An immediate follow-up learning target will be I can find the average value of a function. And finally, today we're going to estimate area with not a rectangle approximation method, but using something called the trapezoidal rule. So the mean value theorem for definite integrals, as we look right here, here's a theorem. Very, very, very importantly, we need to have f is continuous on a closed interval. If we don't have f being continuous on a closed interval, this theorem is not applicable. But if we do, then there will exist a z value on the open interval from a to b. Z is really an x value, such that the definite integral from a to b of f of x dx is equivalent to f of z, plug in that x value of z and you'll have a y value, times b minus a. And that can look rather strange, but geometrically it can make some sense. Geometrically, let's just say that f is continuous from a to b, and we're going to look at the net area in green here. Here it would all be a positive area. What you're saying is there is some x value, which we could call z, such that when we plug that into our function, when we get a y value, that y value, we could create a rectangle, and we'd have a rectangle that is f of z units tall, b minus a units wide. So that base times height, that area of the rectangle, would actually be equivalent to the net area from a to b. That is really what the mean value theorem for definite integrals is all about. So let's take a look at example 1. We're integrating from 1 to 4 of x squared dx. By the way, 63 over 3, it's really 21, isn't it? They're saying, hey, could we find a number z satisfying the mean value theorem for integrals? Well, first off, f of x, which happens to equal x squared, is a polynomial and is continuous on this interval, on the interval from 1 to 4. So what do we know? We can say there exists a z on the open interval from 1 to 4, such that this integral from 1 to 4 of x squared dx would equal f of z times b minus a. Well, guess what? Your a is equal to 1, your b is equal to 4, so that's 4 minus 1. Well, we already know that this left-hand side, we could have figured it out. It's 21. So 21 is equal to f of z times 3. I'm going to divide both sides by 3. 21 divided by 3 is a 7. But what is f of z? If f of x is equal to x squared, f of z would be z squared. So when we take our square roots, plural, we'd get z is equal to plus or minus the square root of 7. However, what we have to be aware of is z must be on that open interval from 1 to 4. So we reject z equals negative radical 7. That doesn't fit in the interval. The answer that we're looking for, we're trying to find the z satisfying it. It's that x value. All right, well, now let's just take a look real quickly at just some basic arithmetic. Consider the average of the numbers 7, 8, 9. What you do is, of course, you add 7 plus 8 plus 9. Then you divide by how many numbers you have. Now, what we're about to do is look at the mean value theorem for integrals in a different light. Look at what we normally write on the left side, the right side. I'm going to put it on the left side right now. If we had that, what if we solved for f of z and divided by b minus a? So we had something like so. And we're going to break this down into a Riemann sum. We're going to say, look, this integral is really saying, let's have the area of a rectangle, f of a w sub k times delta x. And by the way, we're going to have an infinite number of rectangles as well. So we could bring that b minus a in and say we have delta x all over b minus a inside. So we've got f of w sub k times that. However, guess what I want you to take a look at? Because of what we learned with RRAM, LRAM, when we were doing Riemann sums with rectangle approximations, you could very quickly solve for what delta x all over b minus a is. I could multiply both sides by 1 over b minus a. And here this would cancel out. You'd get 1 over n. And then you'd have delta x all over b minus a. Look at that. So what we're getting at is this delta x all over b minus a, it's really 1 over n. So that's another way we can put that in there. So you look at this, you'd say, well, how does that help? Well, remember, we're going to have n sums here. We're going to go from 1 to n. So we'll have f of w sub 1, f of w sub 2, all the way to f of w sub n, but we're dividing by the number of terms that we just added up. Right here, this is sure going to look like what we just did, finding the average of 7, 8, and 9. If we had 3 terms, we divide by 3. Here we have n terms, we divide by n. You can see this as an average, of course, the average of the n terms. Well, you could say, well, really, you're going to have an infinite number of rectangles, an infinite number of heights. Yeah, but what are we talking about? It's the average of these. What kind of values are these? They're f values. That leads us to the following, and you want to memorize this. This is far more common and far more important than what we had talked about earlier. The mean value theorem for integrals is very important, but it's this change in the mean value theorem for integrals that is most often referred to. We are defining the average value of a function to be 1 over b minus a times the integral of a to b of f of x dx. As long as f is continuous, this is how you find the average value of f on a closed interval. Integrate from a to b of f of x dx. Out in front, multiply by 1 over b minus a. Tremendously important concept. Speeding things up, example 2, find the average value of f of x equals x squared from 0 to 3. You can see that this, of course, is a continuous polynomial. And as we look at this graph, we can see plugging in a 0, my y value is 0. Plugging in a 3, my y value is a 9. There are billions, infinitely many y values that we have. You might wonder what the average y value is. It's really tempting to just say that you're going to average 9 and 0. But as you can see, you've got some points way down here. It seems like the curve stays low for a while. So look, the average value is going to be 1 over b minus a, integrating from a to b of f of x dx. We want to have that memorized. Our a is 0, our b is 3. So this is 1 over 3 minus 0. We're going to integrate from 0 to 3. Here's our x squared dx. So it's really not that bad of a problem. Let's take our antiderivative. bump x squared up. We'll make this x to the third and then divide by a 3. And my goodness, 1/3 and a 1/3, that becomes a 1/9. And then we're going to plug in 3 to the third minus 0 to the third. So what do we get? 1/9 times 27. We're going to get an average value of 3. So that's how we can work through this very quickly. The average value of a function can be found nice and quickly. Another major topic that we're going to talk about. Last chapter we worked extensively with LRAM, RRAM, and MRAM. Today we're going to look at the trapezoidal rule. By the way, the trapezoidal rule is the average of your LRAM and RRAM, if you can believe that. That can be a little surprising, but it is in fact true. Very, very, very importantly, you want to remember the formula for the area of a trapezoid. The area of a trapezoid is 1/2 base 1 plus base 2 multiplied to the height. But this trapezoidal rule is only going to be able to be used, at least this formula that we're going to be giving you in green, is only going to be used when delta x is constant. And delta x is still what we learned last chapter, the length of the interval, b minus a, divided by n. So here is a formula if your delta x is always the same. Trying to make sense of that will be where we're going next. But look what we have in green. It's b minus a all over 2n. And then in these brackets, we'll have f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2. It would be 2 times f of x sub 3, all the way to the very last value, f of x sub n. But notice this one isn't doubled. I want you to pay close attention to how the first and the last f values don't have 2's in front. And that can really make kids wonder what in the world is going on. Tell you what, I'm going to just begin to work this out, and let's go ahead and see if we could make some sense of this. I'm going to use some different colors, and I'm hoping that that will help you out. So let's have in blue. So very often kids will even look at this and say, I don't even see a trapezoid. Guys, we're so used to seeing trapezoids looking something like this. These trapezoids will be turned on their sides, and we're always going to have a right angle. So in other words, this will be my base 1, this will be my base 2 right here. Delta x is your height. Delta x is going to be your height. So here's your first trapezoid. We're going to follow this basic property from what we learned back in geometry. 1/2, well, what's your first base? Well, it's a y value. It's f of x sub 0. Plus, what's your second base? Well, you can see these are your parallel sides. That's f of x sub 1. And what's your height? Well, your height is actually delta x. Let's take a look at our second trapezoid. Maybe look at this in red. And we can say, well, I'm going to do 1/2. Well, I'll have f of x sub 1 plus f of x sub 2. You can think, well, what's your height? Well, again, that's going to be delta x. Maybe we could keep going, and maybe you see a pattern emerging. As we look over here, and as we draw another rectangle right here, look at your bases. We'd say, here's 1/2. We'd have f of x sub 2 plus f of x sub 3 times delta x. So here's your third trapezoid, and over here was your second. And we're going to keep going, but we're going to make a new video picking up from here to see if we can connect to what we saw up above.